Earlier this year, Japan made history, but not for the reason you may think. Yes, it landed a spacecraft on the moon for the first time, joining the ranks of the USA, Russia, India and China, who came before them. But JAXA's mission was much more than that. They achieved such a precise landing on the moon, it would be the equivalent of successfully shooting a skin cell from London to Cairo and having it land on a specific grain of rice. In the run-up to the launch, it was this insane ambition of precision engineering that had everybody talking. Once JAXA touched down, the headlines back on Earth shifted. Nicknamed moonsniper for its stealthy precision, its whole mission was mainly to demonstrate how precise of a landing we can now pull off. As such, the tiny spacecraft was not meant to survive the extreme conditions of a lunar night, and yet, somehow, it has survived 3. Baffling scientists, this resilient craft kept waking up and sending back data and images from the lunar surface. Oh, and it's also upside down. I'm Alex McColgan and you're listening to the Astrum podcast. Join me today on this topsy-turvy ride as we dive into the details of JAXA's first moon landing, what has kept the moonsniper functional through 3 lunar nights, and how much pinpoint landings will change the future of lunar exploration. The Smart Lander for Investigating Moon, also known as SLIM or moonsniper, is a small, lightweight spacecraft about the size of a passenger vehicle. Its mission is to analyze the composition of olivine rocks near the Sheppard crater, some 200 miles south of the Sea of Tranquility, where Neil Armstrong took his famous small step. This landing zone stands on ground ejected by the nearby crater, giving researchers a chance to study lunar rock without having to drill. By analyzing the rocks there, JAXA hopes to learn more about the moon's origins, interior and formation. SLIM also carried 2 tiny lunar excursion vehicles, LEV-1 and LEV-2. They were designed to deploy from SLIM and gather some of their own data and photos. Beyond its scientific aims, SLIM is also a showcase of the latest in engineering and mission operations. It aimed to demonstrate how a small explorer could execute accurate lunar landing techniques. This would accelerate the study of the moon and other planets by using a lighter, more precise exploration system, able to land in treacherous, rocky terrain too difficult for larger crafts. To understand why this is a big deal, it helps to have some historical context. The first thing you have to know is that only about 43% of lunar landings are successful. Past lunar missions faced huge limitations in landing accuracy, mainly constrained by technology and the lunar environment. For example, it took the Soviet Union a dozen attempts before they finally landed Luna 9 on the moon. Similarly, NASA's Ranger series took 6 tries before achieving success. The absence of an atmosphere on the moon means that landers rely solely on engine thrust for descent, complicating the ability to adjust trajectories accurately during landing. The craft must touch down at near zero speed to ensure no instruments on board get damaged from the impact. Every single Apollo mission landed dangerously close to rocks, craters, or slopes that could have caused serious damage, with very limited ability to make adjustments in real time. The Apollo missions also all landed on the near side of the moon, close to the equator and in almost perfect lighting conditions, to make touchdown as safe as possible. The downside of this, though, is that NASA was always sending spacecraft to the same patch of moon, meaning actual exploration of the surface was limited to this specific landing zone. If we could make a spacecraft capable of landing in a super precise landing zone, we could send it to explore whatever and wherever we like. Scientists would be able to carry out targeted studies of different rocks and soil types without relying on rovers to travel long distances. This reduces mission complexity and cost, while opening avenues to explore new lunar regions. Moonsniper's mission cost $120 million. For comparison, The 4 lunar rovers built for Apollo 15, 16 and 17 cost $38 million to develop back in 1972, which would be about $286 million today. More recent rovers, such as the Chandrayaan-2 and Chang'e 4, cost about $141 million and $180 million respectively. And this is exactly what researchers are working on, with excellent progress. A landing footprint, also known as a landing ellipse, is the area of uncertainty of a spacecraft's landing zone on an astronomical body. Back in 1969, Apollo 11's targeting ellipse was 18.5 kilometers by 4.5 kilometers. Fast forward to 2013, and China's Chang'e 3 launched with a landing ellipse of 6 kilometers by 6 kilometers. In January 2024, a JAXA lander made Japan the 5th country to land on the moon, touching down just 55 meters from the center of its 100 meters by 100 meter target ellipse, a target 8,325 times smaller than Apollo 11's. Let's take a closer look at the technology that made this possible. Moonsniper was able to land as precisely as it did thanks to its vision-based navigation system, which JAXA refers to as Smart Eyes. By continuously capturing images of the moon's surface as it descends, the spacecraft is able to locate itself in real time on orbital maps made by data from other lunar rovers, including NASA's LRO, India's Chandrayaan-2, and Japan's Selene. These positions were then matched to a broad map encompassing its location to determine the exact landing site. By processing the images in real time, Moonsniper can adjust its trajectory, literally on the fly, enabling it to hit its target with pinpoint accuracy. Weighing just 200 kilograms without propellant, a successful SLIM landing would demonstrate that small, lightweight spacecraft can accomplish complex lunar exploration missions. Except, SLIM didn't exactly stick the landing. While JAXA managed to land the craft on target, it sort of toppled over at the last minute. But after such a precise approach, what caused this grave malfunction? On the 6th of September 2023, JAXA launched SLIM on course for the moon. It arrived in orbit on Christmas Day 2023 and eventually approached for landing on January 18, 2024. As Japan watched on intently, the approach was live-streamed. One mission team member dubbed the deceleration to landing as expected to be a breathless, numbing 20 minutes of terror. As it made its descent to the lunar surface, one of SLIM's 2 main engine nozzles mysteriously detached 50 meters above the moon's surface. This off-center thrust caused it to gain lateral motion, which it tried to stabilize unsuccessfully with its smaller thrusters. The incredible thing is that SLIM was able to identify the anomaly in its descent and find a safe spot to touch down, avoiding a crash. SLIM tipped over onto its nose, as seen in images from one of 2 autonomous probes SLIM released before it touched down, with its panels pointing away from the sun instead of up towards it, as planned. Without light from the sun, it was only a brief matter of time before the craft would run out of energy and shut down. After taking some more photos, and with just 12% power remaining, JAXA decided to switch the craft off in hopes of a possible recovery when the sun's angle changed. Indeed, just 10 days later on January 29th, that's exactly what happened. For 2 short days, SLIM was able to power on using energy from the sun, which had since shifted its angle in the sky. However, the elation was short-lived by the JAXA team, who knew the lunar night was approaching, which would likely spell the end of our revolutionary little spacecraft. Lunar nights are a challenge to all moon-bound missions. They are absolutely brutal, and it isn't uncommon for lunar craft not to survive a lunar night. For example, the first US craft to make it to the moon in 50 years, the US lander Odysseus, failed to awaken following a lunar night. Much like SLIM, it malfunctioned on approach and landed on its nose in early 2024. Despite going into hibernation mode for 3 weeks, it did not wake up again. Since the moon doesn't really have an atmosphere, there's nothing to stabilize its surface temperature. During a lunar day, when the moon is facing the sun, temperatures can reach 121 degrees Celsius. During a lunar night, the moon is plunged into total darkness, and temperatures drop to an average of minus 180 degrees Celsius. That's quite the whiplash for our little lander. What's more, days and nights on the moon aren't like the 12-hour days and nights on Earth. They last 14 days each. That's a fortnight of searing heat, followed by a fortnight of total freezing darkness. SLIM wasn't designed to withstand a lunar night, so on the 31st of January, the mission team put it into a hibernation state for the next 14 days. It was not expected to survive, but the hopeful crew decided they'd try to establish contact after the sun rose again, just in case. On the 26th of February, JAXA attempted to re-establish contact with SLIM with few expectations. Imagine their total shock and elation when SLIM responded. Their miracle moonsniper survived its first lunar night and started sending pictures back to Earth. It gets even better. After 2 weeks of data and image collection during its second lunar day, JAXA set SLIM into hibernation once again. Surviving one lunar night is no small feat. No one expected SLIM to survive a second one, but somehow it did. On the 21st of March, JAXA confirmed they'd received more communication from SLIM following its second lunar night. The pattern continued in late April, when even more pictures were sent back from the lunar surface following its third lunar night. SLIM had totally defied the odds, maintaining its functionality through intense levels of heat and cold, which could destroy most electronics not specifically designed for these conditions. Somehow SLIM still managed to send back data and images following 3 lunar nights. These images of the surrounding moon rocks will help researchers better understand lunar geology. In one image, SLIM took a close-up photo of a moon rock called Toy Poodle, using a special multiband camera. Although it was a little blurred, geologists were able to use the image to distinguish between the different minerals that make up the rock, giving clues as to how the moon formed. Following the 4th lunar night, JAXA attempted once again to re-establish communication with SLIM. However, as of the 27th of May, they've been unable to confirm successful communication with the moonsniper. Despite all its heroic efforts, it's likely it has fallen silent once and for all. Still, JAXA's first lunar touchdown is a breakthrough in interplanetary travel. Demonstrating the feasibility of such pinpoint landings opens the door to many other possibilities. One key area of interest to scientists is the South Pole Aitken Basin, where the moon's mantle is suspected to have once been exposed on the surface. NASA is also planning a return to the moon in 2026 with the launch of their Artemis missions. Pinpoint touchdowns like the one executed by moonsniper may be vital in helping us get to water ice lying in permanently shadowed regions, which until now have been inaccessible. Moonsniper stands as a testament to all the progress and innovation we've achieved since the last lunar era of the late 60s and early 70s. As both public and private interest in revisiting the moon continues to grow, missions like Moonsniper give us a glimpse into what the second lunar era might have in store for us. Well, that's all we have time for today. I hope you've enjoyed listening to this podcast about the incredible, if a little unorthodox, moonsniper. If you've enjoyed what you've heard, please feel free to follow us for more podcasts on other fascinating space topics. But for now, I'm Alex McColgan, and this has been Astrum. All the best, and see you next time.